Hello, everyone. This is Mohamed Ibrahim. And in today's presentation, I'll give an overview of high performance CNN inference acceleration on FPGAs, the tool that we have, which is called Hpipe, and how we extended it and enhanced it in a lot of different ways to enable different applications and extend its performance even further. So let me start with so convolutional neural networks, or CNNs, are a class of artificial intelligence that is specialized for vision tasks with numerous applications such as face recognition, and more recently, it has been used for COVID-19 screening. CNNs require billions of computations, which makes it challenging to deploy them on traditional processors. Fortunately, those computations are inherently parallel and often friendly to low operand precision. And this motivates building customized hardware accelerators on several platforms, such as ASIC chips and GPUs, to accelerate those computations. Recently, field programmable gate arrays, or FPGAs, have become more popular as a platform to accelerate CNN computations, as they can be rapidly configurable, and they are highly customizable and high in power efficiency, which makes it practical to tune the accelerator for the specific needs of the problem in hand or the application in need. So how is CNN inference performed on FPGAs? So there are two kind of main approaches in accelerating CNN inference. So the classical and more common approach is a processing element approach, where you have this array or matrix of processing elements, and then you have your CNN, and you sequentially accelerate the layers on the matrix of processing elements. And this style could have some inefficiencies because your PA matrix is designed to accelerate all the layers, so it could be inefficient for some layers. And this motivates the second style, which is called a data flow architecture, or data flow style. And this style, instead of having this fixed, unified set of processing elements, instead we have a processing element or a functional unit, we call it, for every layer in the CNN. And having this makes the accelerator much more efficient because you design the PE, or the functional unit, specifically for the needs of the layer without having any inefficient modules or blocks. And you can pipeline those layers on the FPGA, and this is very suited for FPGA because you have cheap registers over there. So this takes us to today's topic, which is Hpipe. So Hpipe was developed at the University of Toronto by a former student called Matthew Hall. And ever since, we have been extending and enhancing it. So let's give an overview over Hpipe. So let's first focus on the architecture. So Hpipe is a data flow architecture that builds a customized hardware unit for every layer in the CNN. And this tuning of the layers makes Hpipe much more efficient than generic accelerators, and leads to high compute density. Hpipe pipelines across those layers, which means that all the layers at some point will be processing concurrently on different parts of the image. And this represents another dimension for parallelism, and this leads to enhanced performance. Between the layers, we have latency and sensitive FIFO interfaces, and we have coarse back pressure signals to ensure correctness of functionality. We also chose certain pipeline stages for every layer and between the layers, and this pipeline is deep and configurable, and it has a lot of physical design considerations, and this leads to achieving high Fmax on the actual device. Hpipe shows us the precision for the different layers, and it could choose low precision such that it does not affect the overall accuracy. But for the results that I show today, it's all using a fixed precision of N16. Hpipe also does not use any off-chip memory, so it places all the weights and biases and everything on the on-chip memory of the device. So on the right, you see this network called SSD Mobile Net V1, which is used for object detection. We'll talk about it later in the presentation. And as you can see, this is the design after it has been placed and routed by Quartus. And the different colors on the FPGA represent different layers from the CNN. and this is an Intel StratX10 device. So you have this unique accelerator for every CNN, and it becomes challenging or even infeasible to design this by hand. So Hpipe has an automatic compiler that understands how to take in a TensorFlow graph and the target resources on the device, and it spits out the Verilog and memory initialization files for the design. During this process, it optimizes the TensorFlow graphs by swapping and merging some nodes, and then it moves to split statically the resources of the FPGA between the layers to achieve a balanced pipeline to maximize the throughput. I'll talk about this in the following slide. And then it generates the RTL files, as I mentioned. So let's talk about this resource allocation stage. So Hpipe is really a pipeline of layers, and the pipeline is fast as its slow stage. So Hpipe looks at the layers, and it looks at those bottleneck layers where their latency or throughput are limiting the overall throughput of the pipeline, and starts to allocate resources to those, mainly DSPs, until they no longer become the bottleneck and they improve the overall throughput of the pipeline. On the right-hand side, you see this graph that has the convolution layers of ResNet 50 and the latency of each layer. And starting with a low DSP target like 700 DSPs, you can see that some layers on the right, they have a latency of 2.6 milliseconds, which limits the overall throughput of the pipeline. But as the compiler goes on, it tries to allocate DSPs to those layers specifically, and it continues until it reaches the target, which is in this case 5,000 DSPs. And by the time it does that, you can see that the pipeline is pretty balanced, and that the maximum latency is below 0.3 milliseconds, which improves the overall throughput of the pipeline. So for the performance of Hpipe, so at the time it was published, it outperformed all prior CNN inference accelerators on FPGAs. And to compare, we put 2-3 architectures here: the NVIDIA V100, the Microsoft Brainwave, and the Intel DLA. And as you can see, at a batch size of 1 on ResNet 50, Hpipe outperforms those other platforms by far. And they are different. They use different precisions. They have different accuracy. But for this only 4% loss in accuracy, we can see that Hpipe achieves very good performance compared to other platforms. So Hpipe is great. It accelerates CNNs and produces very high performance. So we took Hpipe and enabled accelerating other applications such as object detection, which incorporates CNNs but has other modules as well and other blocks. So what is object detection? So object detection is a vision tasks that involves 2 stages. It involves localizing objects or an object within an image and then classifying those objects. It has many real-time applications such as self-driving cars and smart surveillance systems. And for those applications, you need high accuracy as well as high performance. For example, if you're detecting pedestrians, you'll need very low latency and high throughput in order not to hit those pedestrians. So the classical way of performing object detection is performing it in 2 separate stages. So first, localizing the object or the objects within an image and then classifying those. And this is an accurate method, but it's computationally intensive. So instead, there is one combined solution which combines classification and localization in one step. Those are called single shot detectors, or SSD. And the key idea is to have a preset of predefined boxes in certain locations of the image to cover different shapes and different location of the image. In inference, you just compare against those, which saves a lot of computations in the inference stage. So this image will give an overview of the full stack of single shot detectors. So we first have the backbone CNN, which extracts the features from the image, and those are normal CNNs like MobileNet V1. And then we have a new set of convolution layers that are called SSD convolutions. And then those are box and class predictors. Those consume the features and predict coordinates of boxes and their classes. And those boxes and classes are predicted as offsets from the actual location. So we have this state that we call NMS, or non-maximum suppression pre-processing, where we take those offsets and we convert them to actual locations after coupling them with the predefined boxes, or called the anchor boxes. And finally, we have a thresholding process where only boxes above a certain threshold pass this stage. The final stage is we call it non-maximum suppression selection. And in this stage, we remove all the overlapping boxes from the image, and we keep only those that are most likely within an image. So this is our end-to-end object detection system. So we have two parts. We have Hpipe to accelerate the feature extraction, or the normal backbone CNN, the box and class predictions, or the SSD convolutions. And then we collaborated with a team from Arizona State University, where they developed a hardware-friendly non-maximum suppression unit to perform the rest of the operations required for object detection. So the system flows as follows. An input image is first transferred to Hpipe, where the features are extracted and passed to the SSD convolutions, and then the box and class predictions are passed to the NMS pre-processing and the NMS selection module for object detection. And finally, we receive the output as shown on the right-hand side. And we discussed how Hpipe accelerates CNN inference. I'll briefly talk about the non-maximum suppression unit. It has been developed by the team in Arizona State University, but I'll briefly give an overview of that. So let's talk about how NMS work, or traditional NMS modules work. So first of all, most works that we've seen tend to offload the NMS processing to a processor after the FPGA, but in our implementation, the end-to-end system is placed on the actual device. So for a traditional NMS processing, we first have to reshape or manipulate the data coming from the SSD convolutions to a format consumable by the following or the downstream modules of the NMS. And then we take those boxes and classes, as we mentioned, and in the decoding stage, we couple them with the predefined or the prior boxes, and we convert them to actual coordinates in the image. Finally, we push them through a thresholding stage where only a subset of those boxes will pass that have a score beyond a certain threshold. And finally, we go to the NMS selection unit to remove the overlapping boxes. Now, the problem with this approach is that first, for the data manipulation formatting, it requires a lot of memory operations, and it requires storing all the data. And moreover, it puts a sequential dependency on the outputs coming from the convolutions, which means that we need first to finish all the convolution outputs, store the data in the memory, and then perform those data manipulation and formatting operations. And this prevents pipelining the execution between Hpipe and the NMS unit, which can significantly hurt the throughput. The second thing is that this decoding stage involves a lot of nonlinear operations, such as exponentials and sigmoid. And this is expensive to perform on all the boxes coming from the convolutions, where we actually know that after the thresholding, we'll only end up with much fewer number of boxes that will be passed to the NMS selection. So we have done all those nonlinear operations in the boxes, but we actually do not need all of that. So the proposed NMS, proposed new NMS architecture is, so we take those predefined boxes or prior boxes and we reformat them and reshape them in a certain way. And then on the fly, when the convolution outputs are coming, we rotate them in a certain manner such that we do not need to perform reshaping or permute operations, which were memory intensive. And doing this, we remove the sequential dependency between the convolution outputs and the NMS unit. So we can continue pipelining Hpipe and doing on-the-fly computations without the need to wait for all the outputs from the convolutions. The second thing is that the ordering of operation has been changed such that the thresholding stage is performed before the decoding stage. And this significantly reduces the amount of computations because after the thresholding, we wind up with a much lower number of boxes that we can now do those nonlinear operations on them without much intensity or without being so expensive. So after doing that, this figure on the right shows an execution trace of our end-to-end system. So the blue boxes represent the SSD convolutions, which are accelerated by Hpipe. And then the green boxes represent, we call them NMSPP or pre-processing. And those are the data formatting, thresholding, and encoding stages. And then we have the pink boxes, which represent the non-maximum suppression selection or the final stage of the end-to-end system. And as you can see, we have a pipelined execution where the data processing by the NMS is overlapping with the SSD convolution acceleration by Hpipe, and only 3% of the time within each image that we have Hpipe completely stalled or not working, waiting for NMS to finish processing. And this is very good, actually, results in very overlapping pipeline execution. So we to test that, we compiled a network called SSD MobileNet V1, which is one of the MLPerf benchmarks. And we ran it on an Intel Stratix 10 GX 2800 device. And looking at the resource utilization that we have, we can see that we're nearly utilizing most of the FPGA resources. Mainly DSPs, we're at approximately 90% of the DSPs, and yet we're achieving very good frequency, which is 350 megahertz. And moreover, if you look at the distribution of resources among the Hpipe and the NMS unit, you can see that the NMS unit is very lightweight, as it consumes less than 10% of the available resources. And this is very efficient to leave most of the resources for Hpipe, which is doing the bulk of the computations in the CNN, to be able to accelerate them in a good manner. So let's take a look at the results. So as I mentioned, we run SSD MobileNet V1 on an Intel Stratix 10 GX 2800 device, and we achieved 609 frames per second and 2.4 milliseconds of end-to-end latency on the COCO validation dataset. And for accuracy, the metric for measuring accuracy for object detection is mean average precision, or MAP. And we achieve actually a score of 22.5, which exceeds the MLPerf quality target of 22. And comparing our work to other works, specifically to the prior state of the art, we achieved 4.4x lower latency and 1.5x higher throughput than the prior state of the art, while maintaining comparable accuracy. So now that we discussed Hpipe for accelerating object detection, now we'll move to scaling Hpipe to multiple FPGAs to further improve its performance. So Hpipe is great. It produces high performance CNN accelerators, but it has some limitations. First, as part of the architecture, it has to fit all the parameters on chip. And this is a challenge, or sometimes makes it infeasible to accelerate those large CNNs such as ResNet 101 or ResNet 152, whose parameters cannot fit on the memory of a single FPGA. And the second thing is that a single FPGA has a limited number of resources or a limited number of DSPs, and this can limit the performance for those compute-intensive CNNs. So a good solution, or promising solution for that, was to scale Hpipe to multiple FPGAs. And keeping the same architecture of Hpipe is very useful to have this pipeline, deeply configurable architecture that leads to high compute density and high Fmax. And then scaling to multiple FPGAs, we have more memory to store the parameters of those large CNNs, and we have more compute resources to achieve to push the performance of Hpipe even further. So now it's even more challenging than before to have to do this by hand, because now we have a unique accelerator for every pair of a CNN and a multi-FPGA system. Might have 2 FPGAs, 4 FPGAs, 8 FPGAs. So we have for every set of a CNN and a multi-FPGA system, we have a unique accelerator. So we need automation. So we have this end-to-end flow that takes a CNN model or a TensorFlow graph specifically, and a description of the multi-FPGA system, such as the number of FPGAs, how they are connected, the resources on each FPGA, and so on. And then it goes into this partitioning stage where it decides which layers on the CNN go on which FPGA and how much resources they are allocated. And under the hood of this partitioning stage, we have multiple stages. We first optimize the graphs, just similar to the normal Hpipe flow. And then we statically split all the resources of the multi-FPGA system combined. So we treat the system as a single giant FPGA, and we split its resources between the different layers. But in reality, we have multiple FPGAs. So we have this additional stage of assigning nodes where we go and take some nodes and place them on a certain FPGA and so on until we finish assigning all the nodes to different FPGAs in the system. Things can go wrong, so we have this legality check to make sure that we do not, for example, we do not assign a node or a group of nodes on a certain FPGA that require more resources than what's available on that FPGA. So I'll talk more about the node assignment stage. How do we decide which layers go in which FPGAs? So our partitioner is resource driven, mainly driven by the number of DSPs and VRAMs that each layer consumes. And we have 3 approaches for that. So if you look on the right, we can see a ResNet 50 graph that shows each convolution layer and how much multiply accumulates and weights it requires, how much compute, how much memory it requires. And the first approach that we use is called the greedy forward approach. And in that approach, we just move forward in the network and we try to pack as many layers as we can on an FPGA before moving to the next FPGA, as you can see. While this approach is good for small CNNs, it's inefficient for large CNNs because, as you can see, while the distribution of compute is somewhat balanced between the layers, the distribution of weights is not balanced. As you can see, the layers at the end of the CNN requires much higher number of weights than the layers at the start of the CNN. And this leads to underutilizing the memory resources, especially on the FPGAs at the beginning of the pipeline. So we have this second approach, which is called greedy bidirectional. And in this approach, after performing this forward pass, we go back in a backward direction, and we try to make use of any leftover resources. For example, in this example, we can fit layer 49 on FPGA 3 going backward, and layer 50 on FPGA 2, and so on, and such that the final shape of the FPGA system takes like a U-shaped path. Finally, we invoke this iterative movement function. If we fail in assigning all the nodes, we invoke this function to try to move some layers between the boundaries of FPGA such that we free some space for the unallocated layers to be placed. In this example, maybe we can push layers 19 and 20 from FPGA 1 to FPGA 2. This leaves some space on FPGA 1 where we can place layers 52 and 53 and complete our partitioning. Now, this flow that I described that takes a CNN multi-FPGA system and partitions it, we can use it in 2 different directions. So first, the more important one is for deployment, where we utilize the RTL generation utility of the baseline Hpipe compiler, and we give it which layers go in which FPGAs, and then it converts it to RTL files and modules that we can then take to Cordis and compile and place on the actual FPGAs. And another important use is exploration. So we developed this performance estimator that estimates the latency, throughput, and resource utilization of a multi-FPGA Hpipe instance. And this is very useful, actually. So I'm showing a couple of experiments here. So on the right, you can see we're experimenting with ResNet 101 and ResNet 152, and on each graph on the x-axis you can see the number of FPGAs. We're sweeping the number of FPGAs, and on the y-axis we're observing how the latency and throughput are affected. Within each figure there are two curves. The blue curve represents the partitioned case, or what actually will happen when we have multiple FPGAs, and the red case represents an ideal case that has a single giant FPGA with the accumulated resources of all of those FPGAs. And in these experiments, we're assuming a Stratix 10GX device, and we're assuming that we're running at 400 megahertz. So looking at those graphs, we can draw multiple conclusions. First, we're showing that we're able to accelerate large CNNs with a certain number of FPGAs. For example, ResNet 101 would require 5 FPGAs at least to be accelerated with Hpipe. Secondly, we're showing that we achieve linear scaling in performance with more resources for a good range before we saturate. And then between the red and blue curves, we can show that we're achieving close to ideal performance, as if our multi-FPGA system is a single giant FPGA. We're not losing anything on the boundaries. And finally, from all of that, we have this fast exploration tool that can tell you if, for example, you have this number of FPGAs and you have this CNN, without going into compiling Hpipe and then compiling Quartus and taking all of those time, we can tell you right away you're expected to get this latency and this throughput for this. Okay, so coming to actual hardware implementation. So and I'd like to thank Professor James and his team for providing the experimental setup that we run on. So this setup was part of the Pegasus project from Professor James's team. And it has 2 Intel Core processors that are talking to 4 Intel Stratix 10 MX devices via Gen 3 X16 PCIe. Each device has 2 Ethernet, 200 gigabit Ethernet ports that allow communication between the FPGAs via low latency 100 gigabit Ethernet. And typically within each FPGA, we actually utilize some of the Pegasus Ethernet modules to handle Ethernet related operations. And then we have our accelerated layers from Hpipe. So this image shows the actual physical setup that we run on with the 2 host machines and the 4 different FPGAs marked in different colors, lots of Ethernet cables between them. And so for the results, so we run all the experiments at 400 megahertz, and we validate the accuracy on the 50,000 images from the ImageNet validation dataset. And we run 3 CNNs that could fit on this setup. So we run MobileNet V1 on single and 2 FPGAs, MobileNet V2, and an 85% sparse ResNet 50. So for MobileNet V1, we showed that we achieve double the performance when moving from single to double FPGAs without losing any accuracy. And the same for MobileNet V2. And for ResNet 50, we achieve 1.8x higher performance when moving from 2 FPGAs to 4 FPGAs. And with this, we can demonstrate that we can achieve linear scaling in performance when we add more resources, more FPGAs. And we achieve linear performance, and this shows that we have negligible communication overhead thanks to this, thanks to the 100 gigabit Ethernet that we're using and the fast Pegasus modules that abstract away all Ethernet related operations and allow us to just compute our computations in a fast manner, just as if we're having a single giant FPGA with just FIFO interfaces between the boundaries. So in comparison to other multi-FPGA CNN accelerators, we're comparing against a couple of works here, 11 and 12, and we're comparing on MobileNet V1 and ResNet 50. First, we know that we're the only one that supports sparsity. We're utilizing 85% sparse ResNet 50, and we're using the highest precision of 16 bits, which allow us to achieve higher accuracy, while the others are using as low precision as 1 bit and 2 bits for waits and activations. For all the experiments, 2 FPGAs are used, except for reference 11, which uses 10 FPGAs. For the devices, we're using a device that's smaller than reference 11, and reference 12 is using the smallest device, but it's using 10 of them. So on the right, you can see the graph for MobileNet V1 shows the latency on the x-axis and the throughput on the y-axis, and you can see that we achieve 1.2x higher throughput and 4.4x lower latency, while at the same time achieving 2% high top one accuracy for MobileNet V1 than reference 11. For ResNet 50, we achieve slightly lower performance than reference 11. We outperform reference 12 by a good margin. And for reference 11, we achieve 5% better top one accuracy. And the gap in performance can be due to first them using very low precision, which causes them drop in accuracy. And then they're using a larger device than the ones that we are using in our experiments. So to conclude my presentation, so I've talked about 3 different topics. So first we have this configurable, deeply pipelined CNN inference accelerator that follows a data flow architecture and accelerating CNNs and produces high performance CNN accelerators. And then we take this and integrate it with a hardware friendly and maximum suppression unit to accelerate object detection. We actually achieve the best performing accelerator with high accuracy. And finally, we show that we're not limited to the resources of a single FPGA. We can push Hpipe, and it scales well when we increase the number of FPGAs, increase the resources to scale the performance. For future work, there are a lot of different topics that can extend and enhance Hpipe and result in great performance gains. So for multi-FPGA, all our experiments target at a point-to-point topology on a homogeneous system of FPGAs, so all FPGAs are the same. We might target heterogeneous multi-FPGA systems with different memory/compute resources on different FPGAs to handle this imbalance in distribution from the CNN layers. The second and more important point, which is exploiting the new strat-extend and extensor blocks. And this is actually being done right now by my colleague, Marius Stan, who has done very good progress on this one. And he will give a session on that next Friday, I believe. And then finally, for the Crossroads project, we have those latency and sensitive FIFO interfaces between the layers of Hpipe. And on the Crossroads FPGA, we have this NOC. So can we leverage this to deliver those latency and sensitive signals? And then for the base die, we have those units. Should we add more compute units, more memory for Hpipe? So those are all questions that can be considered for when designing this architecture. Finally, I would like to thank all of our collaborators. First, my professor, Von Betz, Erico from Intel for supporting this and collecting all of those people for collaboration, Professor James and his group for this nice collaboration, a multi-FPGA setup, and then the Professor Jason and his team from Arizona State University for the object detection work. Some references that I used throughout the presentation, and we have so Hpipe has a published paper, and we have a published paper on the NMS work that was nominated for the Best Paper Award at FPL 2021. And finally, Hpipe is open source, so you can download it and use it right away. It's open source, and it's on GitLab, and I can provide the link for anyone who needs it. Thank you.